My talk is going to be in 4 little vignettes, or 4 examples of when science meets policy. It can get pretty interesting. The first one is on the general issue of the politicization of science, which unfortunately has happened in this country. A few examples of how it might be better served by a bipartisan approach, which is, for example, many countries in Europe take that approach to it. The second one is an interesting one, and that's science isn't static. It's always changing. What we knew yesterday isn't necessarily what we're going to know tomorrow. At least if it's good research, it isn't. Which means that the policy-science interface needs to be dynamic. And that's hard for a lot of politicians to get their heads around. I'll talk then a little bit about the Multi-Party Climate Change Committee, which is what that acronym is. That's the one that came up with the infamous carbon tax, or I should say, much more appropriately, a carbon pricing system. And the last one is a more fundamental one, and that's, I think, what's underneath a lot of the angst about the climate change issue is it really does challenge some very fundamental belief systems in the political side of things, but even beyond the political side of things. So let's go on and talk then about what I call partisan approaches and policy flip-flops, which don't work at all well when you need to get something done. Example 1 is an adaptation example. That complicated little graph there is a graph of projected sea level rise. Very important for us, very important for Queensland, most other states, because a lot of our infrastructure is along the coastline. The jagged line here is actually the observation, and these are the suite of model projections. So the first thing we note is that it's actually tracking near the upper level of those projections. Already interesting information if you need to adapt. And we actually have some information, good information, about how variable sea level rise is around the continent. That's spatially, but it also varies the rate varies in time as well. But again, if you're adapting in a particular place, useful information. And some researchers have also estimated by how much flooding events may increase as sea level goes up. These are pretty big numbers, like this and this. You see this site here just north of here in Queensland. The 2 big capital cities down south have very big multiplication factors. Now you may say, is this for 2 or 3 or 4 meters? No, it's for half a meter, 50 centimeters. So what we're talking about is with a modest sea level rise, 50 centimeters, which I think is fairly certain by 2100. In some of our biggest cities, you're going to see a 100-fold increase or more in flooding events. So that means the engineers, good old engineers, 1 in a 100-year event may happen every year. You're starting to see at least the same type of effect in Queensland. I was up here a fortnight ago talking to the Minister for Environment in the Campbell-Newman government, and one of the messages that he's hearing is people are fed up with cleaning up after one flood and then another one comes along. Well, that's the future that sea level rise is going to bring. So we've got a lot of good science, and it's actually regionally specific, so it's well suited for adaptation. So what's happening on the ground? Well, as we've gone around as a climate commission, we've seen some good examples. Here's a good one in the Clarence City Council. It's a small council south of Hobart in Tasmania. And here you have the ingredients of good policy. You have very active local people who are taking the lead in getting that community together, which is really important. They're liaising with the scientists all the time. They're right up to speed on the latest science. They're very lucky in that the sea level experts in Australia actually happen to reside in Hobart, so they have them next door. But importantly, they have a confluence of policy at the state and local level. So they have a very supportive state government. And so by working through the community, they've actually gotten a lot done in terms of rezoning and so on in areas there you see on the top that is subject to beach erosion. So this is a positive example of how we can actually make good policy, get to grips with these issues, but it requires a lot of cooperation and a singleness of purpose to get there. Here's the opposite example. This is New South Wales, a town called Eden on the south coast of New South Wales. Some of you may know where it is. On the left is a risk planning map, and that's an inundation map, and that blue area is the low-lying area which would be inundated with projected sea level rise this century. The map on the right, which is the same area, is a land use zoning map. So when you look at that, this area here, which corresponds to an area that is at risk from inundation, is zoned for homes, farm buildings, schools, and so on. Now, the problem here is you have two levels of government that are now at loggerheads after the change of government in New South Wales. The local town planners and council would like to do something to change the zoning. They can't get it done because of intervention in the opposite direction by the state government supporting developers. So here we have a case of a very distraught local government because legally they may carry the can, legally, if things are built there and then they are subject to flooding. But they can't do anything about it because they don't have a supportive state government. So here's a case of where a policy flip-flop has occurred with a change of government, and it's very damaging to the way adaptation is being attempted there. Now, it's not only adaptation where this is occurring. As we go around as a Climate Commission and talk particularly to business groups and industry groups around the country, and Jerry Houston, our commissioner who comes from the fossil fuel industry, to put it in Jerry's words, he spends a lot of time talking to the big end of town. And they give an extremely clear, simple message. They do not like policy flip-flops. As long as they have a policy they can live with and gives them some certainty for investment and going ahead, that's what they need. So their worst fear, and they're seeing it at the state level, is the state governments flip from one side of politics to the other. The policy on climate change flips quite radically, even to the point where I understand in your state it's even difficult to use the term climate change. So this makes it really hard for industry. They hold back on investment, they hold back on doing things, because they think with the change of government, everything will be thrown up in the air again. This is quite in contrast to many European countries, particularly in the northern European area, where I do a fair bit of work in Scandinavia, where you look at Norway, you look at Denmark, you look at Sweden, you look at Finland. They all have bipartisan approaches all the way through to the policies. So the government changes, and it does in those countries, but the policy doesn't. Investment goes ahead. So my first point here is that it's very important, right down to the science, to have a bipartisan approach on this. This issue really is a very fundamental issue for human futures. It should transcend politics. In wise countries, it does transcend politics. But we do have some problems here. This is just a last example. I pinched this from Brendan. It's his photograph. This is a really good example of maladaptation. Not exactly sure the real background of why this building was allowed right on top of a beach that's eroding away. I think it's Surfers Paradise, is it, Brendan?
It's Miami. Sorry, it's Palm Beach.
It's Palm Beach. So this is Palm Beach. So here's a good example of how the system is really broken down and allowed a structure. It's not even completed by the looks of it. And it's already being eroded out from under by beach erosion. Number two, assimilating new knowledge. And here's an example that I personally was involved in with the Prime Minister of Denmark at a meeting in Copenhagen just before the big COP15 in 2009. And the issue here is there are a lot of uncertainties around where the science of climate change is going at the really risky end, the high temperature end. A lot of them have to do with these things we call tipping elements in the Earth system. These are parts of the Earth system, the climate system, that can undergo abrupt change when a forcing factor like temperature hits a certain level. The big ice sheets are a good example. I'll talk about Greenland in a moment. And methane coming out of permafrost melting is another good one. Science is moving extremely fast on those issues, changing all the time. I just want to flip through to give you an idea of how the temperature is changing across the planet. It's very uneven. So I'm going to go through 4 decades, 70s, 80s, 90s, and noughties. It's color-coded. The anomaly, it's versus a 61 to 1990 average. So in the 70s, most areas were about average, maybe even slightly below. Watch what happens in the far north. So that's where the action is as far as those tipping elements. So there's the 70s, 80s, 90s, and last decade. So you see that the warming is extremely uneven. And it's biased strongly toward the northern high latitudes and not to the southern high latitudes. So if you just took a transect across the planet from the South Pole to the North Pole and looked at how the temperature was changing, it would look like that. There's the South Pole. And that's where most of us live, but this is where some of the vulnerable areas in the Earth system lie. So the issue is they're warming at more than twice the global average rate. So what is happening? Well, if we look at Greenland, here's a case of just a 4-day change in the summer of 2012. It was a very warm summer. Same summer in which you probably heard about the Arctic sea ice dropping to its lowest level ever recorded. Well, this is the surface melt on Greenland. The red areas are where the surface of that ice sheet is melting. And we had virtually complete coverage in the middle of July, which is a concern because there is a tipping point that once you lower that ice sheet, it's about 2 kilometers high in the middle. As it melts and goes down, it gets into warmer climate anyway, simply because of the lapse rate. And you will hit a tipping point at which you'll be committed to losing most of that ice sheet. There's about 7 meters of sea level rise in that ice sheet. So the fact that the loss of ice is not only increasing year by year, the rate is increasing. That is, it's accelerating. We've got pretty good measurements now from satellite altimeters and from gravimetric measurements. And that shows you that acceleration. These are various measurements of the loss of ice, and it's now going down much more sharply. So that's one of the biggest concerns about our estimates of sea level rise. Have we underestimated how fast this could happen? Big implications, obviously, for adaptation. In terms of the permafrost, these purple areas now looking down on top of the North Pole, Siberia, Alaska, Canada. That's where most of the frozen soil is. That's what permafrost is. There's a lot of carbon locked in the frozen soil there, and that's vulnerable as that melts. The landscape looks like this. It's a very soggy landscape. It's a very flat landscape. It's a very cold landscape. Summertime it looks like this. Wintertime it's frozen. But in summertime, at least until the last 30 or 40 years, it only melted down to about 50 centimeters or so. Now it's melting down quite a bit further. And that's exposing soil that hadn't been exposed to above freezing temperatures before. That's what it looks like. That's the profile, the top 50 centimeters or so. That's the frozen soil beneath it. And there's a lot of carbon stored in that frozen soil. To give you an idea, that's the number. Petagrams is the same as gigatons, or billions of tons of carbon. But the most important is it's about double the amount of carbon in the atmosphere today. That's a lot of carbon that's stored in that soil. And it's a good thing. It's locked away from the atmosphere. What's happening, though, is if we look at the risk there, you can see the estimates by experts in the group. By 2040, which is now not so far away, somewhere between 30 and 60 gigatons. By comparison, our fossil fuel emissions are about 10 gigatons of carbon per year. So you're looking at 3 to 6 years worth of emissions coming out of the permafrost. But a worst case scenario as we go is hundreds of gigatons of carbon coming out. So that's the real concern, is that if this takes off, then emission reductions actually won't matter because the climate will keep warming anyway. So we don't want to hit the tipping point where much of this carbon here is activated. So here's some science which is arguing that there is now a reasonable risk at 2 degrees. There's certainly a much bigger risk at 3 or 4 degrees. This was new science about the time 2009. It's more established now, and some of this data is a little bit later. So I mentioned the 2 degrees. This is a sort of a guardrail. It's I think first proposed by the EU, fairly widely accepted now in negotiations, although the small island states have long argued that that's too much for them and they'd prefer 1.5. But basically the argument goes like this. There's a number of risks as the temperature goes up that you might talk about. Risk to ecosystems. The second one is risk to extreme weather events of the type we've had around Australia this summer. This is actually important because this really is where a lot of the human impacts occur. And there's some other different types of impacts that occur as well. This was the science in 2001. And this is largely the state of the science when the 2-degree guardrail was negotiated and largely agreed. The science was then updated for the 4th assessment report. Didn't get into the report, but it was published in the peer-reviewed literature in 2009. And when you look at that 2-degree guardrail, that's what it looks like in 2009. So the new science is saying, you see the red is the risky bit, the red is coming down lower in almost all of those. And for humans, this is the important one, the extreme events. There's now considerable risk even below 2 degrees of heat waves, floods, and so on. So now some scientists who are getting pretty edgy, some of my colleagues in Europe, for example, and saying, I don't like this 2-degree guardrail. The science is saying this isn't very smart. Well, this was, and Howard may tell you, this is a difficultly negotiated number. And so we got to Copenhagen, And we had a science meeting about 4 or 5 months before the COP15. So we had a panel at the end of the meeting. That's the Prime Minister of Denmark, Anders Fogh Rasmussen. That's Nick Stern. That's Steffan Romsdorf, who's a colleague of mine, and I'm on the end. And Steffan, in his comments, made the point that 2 degrees is no longer safe. And he made it in a very definitive way, saying it has to be 1.5, there are just too many risks. Rasmussen absolutely blew up on the stage. He just went berserk. And he said, you can't tell us this. We've been working so hard. We're planning everything on 2 degrees. You can't do this. It's not possible. We don't accept it. It was just crazy. And so this is a good example of how assimilating new knowledge. Well, poor old Steffan chose exactly the wrong moment to break the news. But anyway, it's a good example of how knowledge is changing all the time. And so you can't just say, deliver science to the policy sector and go away and say, oh, they know it all. It has to be an ongoing interaction. And it needs to be handled a little bit more diplomatically than what happened there. So that gets us on to the Multi-Party Climate Change Committee. So this is the committee. You see the members there. It was chaired by the Prime Minister and the Treasurer and the Minister for Climate Change from the ALP. There were 2 vacant seats. The coalition was invited to join. They didn't join in the end. 2 members of the Green Party and 2 independents, Rob Oakeshott and Tony Windsor. The interesting thing is they actually invited 4 independent expert advisors into the committee. So we sat in the cabinet room and took part in the discussions, which is quite an experience. I'd have to say the most influential was undoubtedly Ross Garnaut, who's probably well known to most of you. He's the economist. Has had a long and distinguished career in terms of public policy. But also Patricia Faulkner was there for social equity issues. And one of the big reasons that we had a very good outcome in terms of the people with lower incomes actually were looked after very well. And I think in a very innovative way, not just through handouts, but through changes in the taxation system. It was basically her pushing for this that got that through. Rod Sims represented the electricity generation sector, which was arguably the sector that was going to be most affected by a carbon price. And I was there for science. So we went through this process. It turned out that one of my jobs was to update the science for the committee, which I did. About the time I completed that, the Climate Commission was formed, and I joined it. So I folded that in. We presented the PM with our first Climate Commission report on the science of climate change. And that did provide an underpinning. I guess to show that they were fair dinkum, I was allowed to make a presentation to the group and was given a half an hour, which is a large amount of time when you're talking about the Treasurer and the PM and so on. I think it went over pretty well. This is one of the slides I showed them. It's very important for policy. What this slide is showing is going back to the 2-degree guardrail. This isn't a temperature graph, this is an emissions graph. And just so you're not fooled by the numbers, that particular analysis used carbon dioxide for the numbers, not carbon. That's why the emissions look bigger. They're, in fact, the same emissions I showed you earlier. What we're showing here is if we want to have a good chance of observing that 2-degree guardrail, there's only a certain amount of CO2 that the world as a whole can emit before we're going to go over that 2 degrees. What this is showing is that the year it peaks is incredibly important for the rate at which you must reduce afterwards. It's a surprising, highly nonlinear effect. There's only 4 years here and 5 years there, but the rate goes between 3.7 and 9 at the maximum down those slopes. 3.7 is really hard. Think of reducing emissions 3.7% every year. We're going for 5% by 2020. Think of 3.7 every year, and that's the best case. Well, we've missed that because we would have had to have peaked at 2011. These are global aggregates, and the world obviously hasn't done that. But if it's left till to 2020, then we have 9% per year at the steepest. And that's basically impossible. That's a wartime footing. So this is really critical information. And the point I wanted to make to the PM and the others was, you got to think beyond 2020 if you're really serious about the 2-degree guardrail. So that's a simple message, but it actually hadn't been thought of very much, I don't think, in the policy sector. There's so much focus on Kyoto, then on 2020. This is some work that Brendan led, and it's going to come out. I think the paper's accepted now for Nature Climate Change. Very simple, and that's trying to show how the terrestrial carbon cycle works with relation to fossil fuels. I'll get to the policy point in a moment. Science is pretty interesting. This is before we ever thought about fossil fuels, when we were just hunter-gatherers. There's a natural flux of carbon, both directions between the atmosphere and the land, and it's pretty much in balance from year to year. Same thing with the atmosphere and the surface ocean. And over longer periods of time, stuff goes down into the deep ocean and up wells from the deep ocean. But if you look at atmospheric CO2 for the 10,000 years after the last ice age, 12,000 years, it's been very steady. It's wavered a little bit, and it's due to natural variations in these fluxes. But it's very steady, okay? So what happened with agriculture and with industry? Well, this is what happened. With agriculture, we depleted a fair bit of the carbon from the land, okay? And we did that really in two ways. We cut down trees and burnt them to make land to grow crops. And by tilling and other activities, we actually released carbon from the soil. So we lost carbon from the soil, we lost carbon from what we call the above ground part. Now, that carbon just didn't disappear. Part of it went up into the atmosphere, CO2 went up. Part of it then came down into the ocean. So basically, it just is redistributed by that active system. So it's part of the active system anyway, and humans simply redistribute it. What this is a new source that's been locked away. So it's different in principle. It's new carbon coming into the active system, okay? And most people don't understand that. So now you got new carbon coming in, and about half of it stays there, half of the remainder goes into the land, and half into the ocean. So you partly refill this sink, or this buffer, as Brendan has called it. You partially refill that, and that's the sink that we see today. But it's balanced by emissions from deforestation, which fortunately have gone down a little bit the last decade. So that's really the system we have today. Now you say, why don't we use the land to offset fossil fuels? Well, here's the problem. Let's do that. Let's shove carbon back down in the land. More trees back into the soil. It's a good thing. All you can ever do, though, is refill that buffer that's left, because there are environmental limits to how much trees can grow, how much carbon you can put in the soil. And so you refill that. But if you say, well, I can emit more fossil fuels because the land is taking it up, then you have more. And I've just colored this gray to make it different. Now you're putting even more carbon into the system. It's going into the atmosphere, and more of it's going into the ocean as well. So now you've got to somehow get that down as well, and now you've exhausted this sink. So the point I was trying to make to the committee was, it's very good to get this down in here for a number of reasons, for productivity of the landscape, for biodiversity, all sorts of good things, and it should happen. But it should be considered as legacy carbon that came from the land in the first place. You should separate out then the fossil fuel. That's different carbon. It's been locked away from the active system. You're just restoring the balance of the active system when you're putting carbon back into the land. So it's really counterproductive to put carbon here and yet shove more new carbon into the whole active system. So the point I was trying to make is, don't try to get out of Australia's obligations by shoving stuff into the land. In the long term, it's counterproductive. We could certainly meet our 5% target by doing so. So that was another bit of science that was discussed in the cabinet room. So how much got through? Okay, I think we did have some impact. Long-term level of ambition. There was no long-term target until this last piece of legislation. It's now an 80% reduction compared to 2020 levels by 2050. Okay, so that's getting it way down. And my argument was, well, if you get to 80%, it's probably not going to be too much harder to get lower, because you will have put in all the infrastructure to get it lower. So we have a reasonable ambition now for our long-term target. Ongoing role of science. Now, the Climate Change Authority was formed to provide advice to the government. The Climate Commission does not provide advice. We're a community engagement group. The authority is a different body, and it does provide advice to the government on targets and timetables. And this is the one I had to argue most strongly about, surprisingly, I thought, because it was mainly going to be populated by economists. And I said, you've got to have an active scientist there so that day in and day out, you're getting updated science all the time. And I'm delighted to say that David Caroli, a very, very good scientist, colleague of mine, was appointed to this role and is now playing that role in the authority. And the last one was this one I was talking about, land carbon. Well, the way we got around that, because they wouldn't give up the idea of offsets, is too much embedded in policy. But you can put a cap, and we did put a cap. Only 5% of your fossil fuel emissions can be, quote unquote, offset, which means basically you are still refilling the legacy carbon. You're not going over that yet. And the argument, we had long arguments about this, and we thought that by really putting the focus on fossil fuel right at the beginning, they're going to have to see that price. They're not going to get it out of their obligation by putting trees in somewhere. We'll actually get the process of investment in the right direction going, and the problem will go away once you get that going. So that's the summary there of what I think came out of that process. But it was an interesting experience for me personally, and I think it's important that well, in my view, and I must admit I'm biased because I was part of the process, I think that the overall outcome of that process was much stronger for having 4 people from outside the political process with various levels of expertise who weren't just consulted. That's the whole point. We were part of the whole process. We were in there talking and debating and discussing all the way through. I just want to close now before I turn it over to Jamie and Howard. One of the things we find, or as I find I go around and talk to people out in the community, is the problem we have so much, the reason we have so much contention around the climate change issue is it does challenge some fairly fundamental belief systems. And unfortunately, what happens then is people take the climate change issue and reinterpret it in terms of their own belief system, whether it's a religious or a political or a philosophical or whatever it is, rather than, in my view, saying, all right, there are many different ways you can approach how you deal with it, but the fact is the basic problem is well understood by science, and that goes beyond whether you're National Party, Liberal Party, Green Party, ALP, whether you're a former East European country, whether you're an African country. What's happening to the planet is basically the same. And so there's a common basis. But it doesn't get interpreted as being the same. So here are some of the examples. So I had a meeting with Senator Steve Fielding when he was there, and this cartoon reminded me very much of what that meeting was like. You couldn't convince him, even with the best science, because he didn't want to be convinced. There's still a nagging doubt in there, no matter what you did. And that wasn't because of the science, it was because it was challenging his political belief system. This is one I commonly see from people in the United States in particular, is we're so big and powerful, we're indestructible. So what, the climate's changing, we'll just engineer our way out of it, whatever we'll do, we'll just keep charging ahead. And this is a fairly common one that you see as well. Interestingly, Petty did this cartoon on the 100th anniversary of the Titanic, somewhat ironic given the rate at which ice is calving off Greenland again just now. And this is the one I think is a really interesting one. This comes from my colleague Catherine Richardson at Copenhagen University. And she's very good at reminding us that science has a long history of challenging humanity and how we think and how we believe. Galileo was a good example of that. He challenged the belief that, that the sun went around the earth. That's what was thought back at his time. And it was obvious if you looked out, the sun goes around the earth. Just like some of the arguments I get from people who think they understand climate science, it's obvious that this tiny gas that's odorless and colorless and a minuscule fraction of the atmosphere can't possibly do anything. I say, yeah, and it's absolutely obvious the sun's going around the earth, isn't it? So there is a role for science to actually unpack what is happening. Darwin's a classic example and a more recent example, still contentious in some parts of the world. And he sort of sorted out where we came from and what our real role is in the natural order of things. And that was a real wake-up call for a lot of people. I think climate change is evoking a similar level of deep emotion in many people. And the thing that I think most commonly underlies it is we're such a small, puny species, and this is such a huge Earth, we can't possibly affect how the entire planet operates. And if we did, why this tiny little gas? There's so much more nitrogen and oxygen. Why this tiny little gas and those other gases that are out there that are causing the problems? And then what really, I think, challenges people is there's been a post-World War II belief in what progress is, which is material growth, material wealth, more things to consume, and so on. And ultimately, climate change at least challenges the way we do this, that we can't keep going on business as usual. And that does challenge a lot of people. Well, I think I've said enough. I'm going to stop there. And those 4 little vignettes, I hope, give us some points that we can discuss about the science-policy interface.